Okay, so it means we have not discussed this, right?
Yes.
Okay, so I'm going to start with this. To refresh our mind what we did last time, we have looked at the PV diagram and TV diagram for phase change of water. Okay, so we look at the TV diagram for a constant pressure line and PV diagram for constant temperature line. Okay, so we have looked at different situations in which when a particular fluid is at the saturated liquid vapor mixture, if I want to determine the enthalpy or the internal energy, what are the various approaches that we need to consider? Okay, for this particular slide, is devoted to compressed liquid. So compressed liquid, we say is a liquid and that is not about to boil. Okay, so a compressed liquid, if you look at this TV or PV diagram, okay, there is the the constant, there is the TV diagram. The region, this particular region is called the compressed liquid region, and then we have liquid plus vapor region, and then we have the vapor region. Okay, so how do you identify when a fluid is in the compressed liquid region? So if you look into this, so we are told that in general, a compressed liquid is characterized by higher pressure. So if you have a fluid where the pressure of the fluid is greater than the saturation pressure at a given temperature, then the fluid is said to be in the compressed liquid region. For example, let's say we have on this particular diagram like this. Okay. Now, this could be our constant, my constant temperature line is this. Okay. So if I have a fluid in this region, in this particular region, then it means that the pressure of that fluid could be, let's say, P. Okay, now the saturation pressure line corresponds to, or the saturation pressure state corresponds to this. This is what called P saturation. And this P, if this P is greater than this P saturation, then it means the fluid is in the compressed liquid region. Okay, so that's this for this particular number one. And for the number two, if you have a fluid in which the temperature of the fluid is lower than the saturation given temperature at the given pressure, then the fluid again is said to be a compressed liquid region. For example, let's see over here. Again, so we have, again, let's say on a TV diagram, temperature, pressure, volume diagram like this, where we have, this is the saturated liquid and saturated vapor lines. Okay, so now this is our constant pressure line. Our constant pressure, P is a constant in this particular state. Now, if I have a fluid that is in this state, you see, and if this corresponds to saturation temperature, this is what we call T saturation. T saturation belongs to this. Okay, and as far as this region is concerned, the temperature at this state will be T. Now, this temperature, T saturation, is much, much greater than the temperature of the fluid at this state. So again, then it indicates that the fluid will be in the in the compressed liquid region. You see, this temperature is what we have over here. That's the temperature of the fluid. And then the T saturation corresponds to this. Okay, so this T is less than the temperature of the at the saturated liquid state. Okay, so these are the conditions, two important primary conditions which are necessary to identify the state of a fluid. Okay. So I think one of you have a problem. Let me attend to him. Let's see. And let me see. Ahmed have a problem. So, and let me see. All right. So let us pause a while for them to join the class.
Yes.
Okay, so welcome all those who came late. Okay, so next time I think we should start maybe 10 minutes before the time, maybe around 3:50 or something like that, to avoid this delay and other things. Okay, so yes, I was discussing about the the PV and TV diagram for a compressed liquid situation, and I'm told that whenever you have, let's say, a PV diagram, let's say we consider this to be a PV diagram. Okay, so for all PV diagrams, it means that we're going to have a situation like this. Okay, and then this is our constant temperature line. So a constant temperature line means T is constant over here. Now the pressure keeps on changing as you increase or reduce the pressure will be reducing, but it will be at a constant temperature. This is what we call a PV diagram. Now, on the PV diagram, if we have the pressure of a fluid, let's say at this section, okay, at this demarcation. So let's say its pressure is given by P, okay? And then the saturation pressure that corresponds to a particular temperature is also over here. So this is what called P sat, P saturation. Now, whenever you have a fluid in this section, in a rigid vessel, and its pressure is P. Now, the existing pressure over here is normally less than, the existing pressure, if the existing pressure is greater than P saturation, then it means that the fluid in this section is in the compressed liquid state. Okay, in a similar situation, if you consider a TV diagram, what is TV diagram? A TV diagram is a diagram that consists of a constant temperature line, okay, sorry, constant pressure line. And so on a TV diagram, we also have a situation like this, where we have, this is the constant pressure line. Okay, P is constant. Now again, if I have a fluid over here, we all know that this portion corresponds to T saturation temperature. Okay, so saturation temperature is the same as the boiling temperature for water. Now, if we have a fluid in this region whose temperature is given by T, okay, so the temperature of the fluid here is T. Now, this T, since it is then it will be the compressed liquid region. That is. So again, if we, let's say we find ourselves in this particular state, I have a specific volume over here, and this corresponds. Now, if I have a specific volume, which is V over here, so the V that corresponds to the volume and this region, since it is less than the VF, okay, so then it means our fluid will be in the compressed liquid state. So if you look over here, this V is less than VF, so it is correct. So we have the V over here, that is the V for this fluid, which is less than the VF. Okay, that's the specific volume at the compressed liquid state. Sorry, This is the specific volume at the saturated liquid state, and the specific volume at the saturated vapor state corresponds to Vg. So the same applies to U, internal energy, and enthalpy, and so on and so forth. So there's not so much things to talk about over here, except that we have to solve some questions to understand the concept over here. So like I've told you, I'll find some way in which we can solve these questions. Okay, so maybe I'll develop a YouTube discussion on this particular tutorials, and then I'll forward to you, and then you can follow it. Okay, so I will not waste so much time on this. Now let us move on to ideal gas. So ideal gas is a very broad topic, okay, and it's a very important component of thermodynamics. Okay, so an ideal gas or equation of state. An ideal gas basically is a gas that obeys the ideal gas equation or the ideal gas law. Okay, so it is developed fundamentally from important governing equations. Okay, so such as if we take, let's say, a balloon over here. Now, from the ideal gas or equation of state, if we say that if the volume of a balloon is kept constant, then so if you increase the mass of the air inside the balloon, so then will also increase, the pressure will also increase. So it means that if you take a balloon, the pressure in the balloon is always proportional to the mass of the air inside the balloon. So if you pump more air inside, then more pressure will be given to the balloon in this way. Okay, so P is always proportional to mass. Now, also one thing we need to know is that the pressure inside the balloon is always proportional to the temperature. Means that when the pressure is increased, the temperature of the gas inside the balloon also increases. Okay, so this is the important information we need to know, the fundamental governing equations related to ideal gas. Now, if as far as volume is concerned, you see, if I keep on, let's say, pressing this balloon from different angles, I try to press it very hard, okay, applying different forces at different sections, try to compress it. What will happen to the balloon? Its volume is going to decrease because of the decrease in size. And then the pressure inside the balloon is also going to increase. So the pressure and volume, they are inversely proportional. So you see that P is always inversely proportional to the volume. You understand me? So if you combine all these three equations, namely P is proportional to mass, P is proportional to temperature, P is proportional to inversely proportional to the volume, then that gives rise to this particular equation. So the combination of these three equations gives us P is proportional to the mass times the volume, mass times the temperature divided by the volume. Now, if we remove this proportionality sign, we need to introduce what we call a constant. And this constant we call the ideal gas constant. So the ideal gas constant is given by R. You understand? So the moment you remove the proportionality sign, immediately we need to introduce a constant. So we can rearrange this equation and tell that PV is always equals to MRT. Okay, so MRT over here. So that gives us in the next slide. Yes. So that's the equation of state of an ideal gas is given by this. Okay, so this equation is, or all ideal gases obey this law. Okay, so what are ideal gases? Like I've told you, all ideal gases are gases that obey the law PV equals to MRT. Example of ideal gas: carbon dioxide, nitrogen, air, all these things are ideal gas. Now, steam is not an ideal gas because steam does not obey the law PV equals to MRT. So whenever you have a question involving steam, or water or even refrigerant, don't be attempted to use this equation to determine any parameter, because those fluids are not ideal gas, so they don't obey this law. So all ideal gases, strictly, they obey this law. So if you have any question related to an ideal gas, then definitely you feel free to use this particular equation to determine either the pressure, volume, whatever it is. Okay, so these are the parameters associated with the ideal gas equation. So you have the ideal gas constant temperature in Kelvin, this is the volume, we have the pressure, and then the mass. Okay, so in order to make the equation applicable to all ideal gases, a universal gas constant, Ru, is introduced. So what is this universal gas constant? Universal gas constant is defined through the ideal gas equation, which is given by this. So we have ideal gas equation equals to Ru divided by mass. This M is the mass of the molar mass. Or sorry, is the molar mass of the ideal gas. Okay, so this universal gas constant is for any gas. It's a constant value. So let's say if I want to find the ideal gas constant for, let's say, air, ideal gas constant for air or oxygen. Okay, so this gives me Ru divided by, let's say, the molar mass of air. Okay, oh yes, we have it over here. So the ideal gas constant for air equals to universal gas constant divided by molar mass of air. So this is universal, this is a constant parameter, it does not change. Okay, so then the mass of the air is also given. So ideal gas constant for air is this. You understand me? So the ideal gas constant for air is different from ideal gas constant for oxygen. Similarly, the ideal gas constant for hydrogen could be also different from ideal gas constant for carbon dioxide, and so on and so forth. So this is a general form of equation which is used to determine the ideal gas constant for different ideal gases. Okay, so now, if you want to express this equation in terms of mole, we could also do that. Okay, so we only need to represent the what do you call it, the mass over here. Okay, the mass, and then the Ru by and Ru by N times Ru. So here, in terms of mole, is given by this, where N is equal to the number of mole of the ideal gas. Okay, and then M is the molar mass of the ideal gas. Okay, so and by definition, we can use this equation. If we know the number of moles of the ideal gas, we could use this. You understand me? Where this is the universal gas constant. If we know the mass of the ideal gas, then we could use this equation as well. Okay, so these are the two approaches that are available in determining the ideal gas constant for different gases. So now let's see the according to, so three names in particular are associated with the ideal gas, namely the Boyle's law, the Charles law, Gay-Lussac's law. We have done this in your what do you call it, fundamental elementary schools. Okay, ideal gas equation that are related to Charles law, Gay-Lussac's law, and Robert Boyle's law, and so on and so forth. So according to Boyle's law, okay, the pressure of a given mass of a gas is always inversely proportional, okay, to that particular gas. In other words, PV equals to a constant. And according to the Charles law, T, the temp or the volume of an ideal gas, okay, is always proportional to the temperature. So then again, we can express V divided by T equals to a constant. Similarly, pressure, okay, is also proportional to the temperature. Okay, so we could express this in terms of this equation like this. So now, let's see again this. Let's see. So again, I'll come back to these particular questions later on. Okay, let us proceed with specific heat capacity. Now, in specific heat capacity, and it is basically, you see, the amount of energy required to raise the temperature of a unit mass of a substance by 1 degree Celsius. Okay, so the term specific heat capacity is very, very important in as far as thermodynamics is concerned. Okay, so we define specific heat is another physical property of a substance. All substances have temperature associated with it. The temperature of a substance is directly measured on is a measure of the motion of the molecules. The greater the motion of the motion, then the higher the temperature, as shown in the figure. Okay, so in specific heat capacity, okay, so we define mathematically by this particular equation. We say that C equals to E. E is the amount of energy, and M is the mass, and delta T is the temperature. So let me give a classical explanation over here. Let's say we have a substance in this closed system. Okay, so then we transfer a certain amount of energy, Q, to it. Now, the amount of energy transferred, Q, is always proportional to the temperature. Sorry, it's always proportional to the mass. Sorry. They're always proportional to the mass of the substance and inversely proportional to the temperature. Okay, inversely proportional to the temperature of the substance. So that if we remove this proportionality sign, okay, so we introduce a new constant called C. And so the equation can be written in this. So let me again, the physical meaning of this is that, let's say the mass of the substance in this particular closed system is M. If you want to increase the value for Q, the more we give M, the higher the Q is going to be. And the higher the delta T, that's the temperature difference. Higher temperature difference is going to give us higher Q. Higher temperature difference means you have initial temperature T1 and final temperature T2. So that is our delta T. So more heat means higher temperature difference. So it means that M and delta T, they are proportional to this Q. So but if you remove the proportionality sign, we introduce a new constant. This new constant is called C. And this, again, is given by times M times delta T. Okay? So now, this C can be defined like this, that C equals to Q divided by M times what? Delta T. Now, this C is what we call specific heat capacity. So what is this specific heat capacity? It is the amount of energy, this energy, required to raise the temperature. Which temperature? This. Of a unit mass of a substance, okay, by 1 degree Celsius or 1 degree Kelvin. That's the classical definition. So that's the definition for what do you call it? Specific heat capacity, as we have explained earlier on. So that's the classical definition. So you see, this is the energy required to raise the temperature of a unit mass of a substance by 1 degree Celsius. Okay, so, and then 1 kilogram. Now, we have two types of specific heat. We have specific heat at constant volume and specific heat at constant pressure. Okay, one thing you need to know also is that, you see, specific heat capacity or the amount of energy required to raise the temperature of a substance depend more on temperature. Higher temperature means higher thermal energy, which is coming into the system. Okay, so we are going to look into individual specific heat capacity. So for volume and then for pressure at constant volume and constant pressure. Specific heat capacity at constant volume is the amount of energy required to raise the temperature of a unit mass of a substance by 1 degree Celsius at constant volume. So this is a constant volume. Constant volume is we have a rigid vessel. You see, so this is a rigid vessel. So that means that the volume is not changing. The volume remains constant. Okay, so the only parameter which is changing is the pressure, internal energy, temperature. Mass is constant, volume is constant. Okay, so we are introducing some amount of heat into this system. So if you transfer heat into rate, the parameters that will change is one, the pressure. So high pressure is going to build up. The internal energy is going to increase because of what? Because of increase in temperature. You understand me? So now we can mention that as far as specific heat capacity at constant volume is concerned, okay, it is defined through the change in internal energy, the ratio of the change in internal energy to the delta T. Okay, so it means that we can express, let's say, yes, so we can express the specific heat capacity at constant volume in terms of delta U divided by delta T. Okay, so now where U is the internal energy, so we can rearrange this equation like this and tell that delta U equals to CV times delta T. So now again, we can mention that U equals to CV times T. So you see here, the internal energy depends largely on only temperature. Higher temperature, higher internal energy. And if you, this is what we call specific internal energy. Specific internal energy. Absolute internal energy means we need to multiply by mass. So because we know that specific enthalpy is equal to absolute enthalpy divided by mass. And specific internal energy, this is small u, equals to absolute internal energy divided by mass. So it means that if you want to determine the absolute internal energy, which is this, you should multiply this small internal energy by the mass. And that's what we have over here. Okay, so, and the next is to define, let's say, specific heat capacity at constant pressure. So specific heat capacity at constant pressure is also a parameter which is defined through enthalpy and temperature changes. So now here, if you look, this is not a rigid vessel. This is a piston cylinder arrangement. Here, the only parameter, sorry, the parameters which are constant. You see here, we have a rigid vessel and a piston. So this piston it moves up and down. It has the ability to move up and down. So because of what, if we add heat to this, the moment you increase or you add transfer heat to it, if the piston moves up, it is going to cancel the effect of the pressure building up. So pressure will remain constant over here. Whereas on the other hand, internal energy is going to increase, temperature is going to increase, volume is going to increase. You understand? So now we define enthalpy. Yes, so note that the substance is flowing, and then the change of internal energy, pressure, and volume can be seen or defined through enthalpy. Yes, very important. Enthalpy is defined as internal energy, the sum of internal energy plus the pressure of a fluid times its specific volume. Okay, so please take note of this equation. It's very, very, very important. that enthalpy of an ideal gas equals to internal energy times the pressure times the specific volume. Okay, so this is defined through this. Now, the specific heat capacity at constant pressure is defined in terms of the enthalpy. So you see the difference. So here, specific heat capacity for at constant volume is defined through this particular equation. So, whereas the specific heat capacity for constant pressure is defined through this particular equation. So that, let's say we can rearrange this equation and tell dH, that's the delta H equals to Cp times delta T. Again, we can express this in terms of specific quantity. We can express it in terms of absolute quantity terms. Okay, so let me see over here. I think I will take a short break and then this equation. Let us explain this. Now, here we have already defined enthalpy as a sum of internal energy plus pressure and specific volume. Okay, so, and